Welcome to Dr. Jed's Continuing Calculus video series. Today's lesson is 4.1 from Rogowski, which is linear approximation. The first question, of course, might be, what is linear approximation? Another word for it is local linearization. So we'll talk about that, try to come up with a formula for it. It's not really as bad as it sounds. Then we'll do an example, talk about how close it is. Notice I'm using L of x for the local linearization. How close is that to the function f of x? Then from this, there's two ways to answer this. One is, how close is the approximation exactly? That's relative error. And how close is it approximately using formulas? And that would be an error bound. We'll talk about that and that one. But first, let's talk about where does the formula come from? What is a local linearization or a linear approximation to a function y equals f of x when x is a? Well, here's the function y equals f of x. The linearization is, well, let's zoom in. If you zoom in, the function's approximately linear. So we'll say L of x is the local linearization of y equals f of x at x equals a. And you look, it's making that linear. But we've seen this before. This does have a name already. This, L of x, is the tangent line. And we have a formula for the tangent line already. So let's write that. Well, actually, before we write that, let's consider how we're going to end up with this. I want to use a point-slope form of this, not the slope-intercept form we usually use. The point-slope form typically goes y minus y naught equals m times quantity x minus x naught. But since I want this to equal some value, the y should equal some value, so I'm actually going to write this part over here. So that's the form I want. So let's stop and think about this. What is m? M is the slope. The slope of this, we already know that. The tangent slope is the derivative at that point. So this is f prime of a. What is x naught? X naught is a. And what's y naught? Y naught is the y value there, which, well, if this is the function, f of x, when x is a, y is f of a. Yeah, it may not have been written quite so perfectly, but it produces the formula we want, which is L of x is f prime of a times the quantity x minus a plus f of a. Now you may wonder, why would we even need this? The thing is, we can just punch this in our calculator anyway. But this is good if you don't want to use a calculator, or if you want to study the theory of how calculators make formulas, or just the theory of functions. So, let's use this as an example. Let's estimate this, 1 over 101, without a calculator. Now, you could probably do that. Maybe you could do that in your head. But let's do it using the local linearization. First, we need a function, because we need the f to find f prime and so forth. So what function would we be using here? I'm going to use f of x is 1 over x. We also need a base point, a. If we're not going to use a calculator, we better pick something we can use, something we can do in our head. Is there an a near 101 that you could figure out the value without a calculator? Hopefully the answer is yes, and hopefully you can see 100 works. Because what's 1 over 100? F of a is going to be 1 over 100, which as decimal is 0.01. Now most of the formula is already done. We need f of a, we need f prime of a. So what is f prime of a? Well, we need f prime. F prime of x is going to be the derivative of that. You can turn that into a power. That's x to the minus 1. Take the derivative using the power rule. You could use the quotient rule. Go to the top times the bottom and so forth. Or you could just know the derivative is minus 1 over x squared. And we don't need to know that at 101. We need to know that at a, so at 100. F prime of a is minus 1 over 100 squared. And again, that's 4 digits in the bottom, 1, 0, 0, 0, 0. So 1 over that with a minus sign, we want a minus 0.0001. So let's put that together. Our linear approximation is going to be minus 0.0001 x minus 100 plus 0.01. Notice this is sort of the curve, y equals 1 over x. If that's x equals 100, we just want to estimate right there. And notice the line is really close. We'll talk about how close in just a second, but let's finish that off. We want L of 101. And we can do that in our heads. Put 101 in here, and we get minus 0.0001 times 101 minus 100, add 0.01. 101 minus 100, that's a 1. 1 times this is just that. Add that onto here. Well, just do a couple digits. We get 0.0099. That's the linearization. That's the linear approximation. That's not the actual value of the function. That's our best guess at it without a calculator. So here's a question. How close really is that? We can answer that two ways. We could say, well, let's punch it in our calculator and get the exact value and compare. We'll talk about that. But first, let's talk about the theory behind it. Let's see, how close should this be? How close could it be? So let's talk about error bounds. In general, if you have L of x equals f prime of a times x minus a plus f of a, so that's the linearization, the local linearization or the linear approximation. How close is that to the original function for a particular x? So again here, this is f of x. This is the linearization. How close is it? Well, notice, as you move farther away from a, either way, it gets more off. That makes sense, right? This is going to depend on how far away x is from a, and it's also going to depend on, well, notice, this is a line. F is not a line. F is curved. So it depends on the curvature of f. I'm putting that in quotes because that's not exactly what it is. Curvature has a more technical meaning, and it's not that technical curvature. It's the amount of curviness we have here. And the more curved it is away from a line, well, if you remember from what we learned about graphs, the thing that describes how much away from a line you are is your second derivative. So it's the second derivative. But it's not actually the second derivative at x. It's the second derivative throughout the whole region. So, the two things that are going to be in this formula for finding out how far away you are is computing how far you are from a. So x minus a is going to be in that formula. That's easy. The other thing is the second derivative over that region. And that's hard to do. That whole region, it's like here, it's here, it's here, here. It's pretty good there, and it gets worse over here. How do you do that? So one solution is take the worst. Take the most of a second derivative you can find in there. In that whole region, take the worst there is, and then just assume that's the worst case scenario for everything. Then you're not going to be off. You're going to be conservative. It's an error bound. It's not the full error. It's a guarantee. So we're going to say, find the worst case of the second derivative, and you use that. Now, here is the error bound formula. The distance from the function to the linearization is less than or equal to 1/2 times, this is what I was saying, the worst case, the biggest of the second derivative between x and a. Or if you prefer, between a and x. Either way. And then multiply by x minus a squared. Now why, there's two things. Why is that squared? Well, that's squared because, step back for a second, this is linear. It turns out that the error bound is going to have one more power than that. Because the linear part is fully taken care of. The second derivative has to do with a second power. If we were to do a quadraticization, whatever you'd say, a parabola, whatever that word is. If we're going to do that, then we would use the error bound one higher, which is a cube. But that's for tomorrow. Right now, we have 1/2 times this times that squared. Where does the half come from? Again, it's in the formula. Right now, you don't have to worry about where it comes from. Let's use it. So, back to estimating 101. So our function was 1 over x. Our a is 100. So the linearization, if you recall, is right here. And plugging 101 into there, we get 0.0099. The actual value, if you use your calculator, which has a magical way of calculating it, 0.0099, 0099, 0099, it goes on forever. So the actual amount of error, if you take the difference here, the first 4 digits are exactly the same. It's that. The error is going to be your estimate minus the original. So we get minus 0.000000990099 and so forth. More interesting than the actual amount of error is the relative error, which is the actual error over the actual value. If you take this and divide by that, you get 0.0001, which is 1/100th of 1%. That's pretty close. The linearization here works really well. It's very close. Why? First of all, because it's a nice function. And second of all, because linearization is good. But let's do the calculation of the error bound. The error bound requires the second derivative. So the first derivative we found was minus 1 over x squared. The second derivative, the derivative of that, again, we could use power rule, quotient rule, whatever rule you want, we can get positive 2 over x cubed. Now, in the formula, we want the maximum of that. The biggest, that is, between 100 and our actual 101. And looking at it, in this case, that's very easy. The biggest that can be is when x is as small as it can be. So that's when it's 100. So the max of f double prime of x, or I'll say f double prime of s, is going to be 2 over 100 cubed. I'm just putting 100 in here. Notice the 1/2 that was in the original formula for the error bound. That half and this 2 will balance out. So the error bound is going to be 1/2 times 2 over 100 cubed times the distance from x to a, so 100 times, or 101 minus 100, squared. Now that's 1, so 1 squared is still 1, that's no big deal. But if you simplify that, the 2's, you get 1 over 100 cubed, or 0.000001. If you compare that with the actual error, 0.0000099, the difference is the error bound has a 1 here instead of that. The error bound is very accurate here. It's not always that accurate. It depends a lot on the function. But the key points here are, what is the local linearization? How do you find a relative error? And how do you find an error bound? Until next time, this is Dr. Jett.